Imagine staring up at the night sky, knowing that hidden among those countless stars are signals, strange, pulsing messages from the depths of space that no one can fully explain. For decades, these mysterious galactic transmissions have left scientists scratching their heads, sparking debates, theories, and even a few wild speculations about what or who might be sending them. Some of these signals repeat like clockwork, while others vanish as quickly as they appear, leaving behind only questions. And here's the thing, we've captured 30 of these enigmatic cosmic whispers, each one more baffling than the last. What if I told you that some of these signals defy everything we think we know about physics? Picture a burst of energy so powerful it outshines an entire galaxy, yet lasts only milliseconds. Or a rhythmic pulse so precise it feels almost artificial, as if something or someone is trying to get our attention. These aren't just random blips in the void, they're cosmic puzzles waiting to be solved, and the theories behind them range from the mind-bending to the downright terrifying. Could they be natural phenomena we've yet to understand, or is there a chance we're glimpsing something far more extraordinary? This is where the story gets even more fascinating. Every unexplained signal carries its own secrets, its own possible explanations, and its own piece of the larger mystery. Over the years, astronomers have proposed everything from colliding neutron stars to advanced alien civilizations as potential sources. But the truth, we're still searching, and that's what makes this journey so thrilling. Together, we're going to explore 30 of the most perplexing galactic signals ever detected, diving deep into the science, the speculation, and the sheer wonder of it all. By the end, you'll see the universe in a whole new light, one where the unknown isn't just out there, it's calling to us. So, are you ready to listen? One of the most famous and frustrating mysteries in the hunt for unexplained cosmic signals began on a quiet August night in 1977. That's when a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary. A burst of radio waves so intense, so unusual, that the astronomer who discovered it circled the data printout and scribbled, "Wow," in the margin, and that's how the WOW signal got its name. What made it special? For 72 seconds, this signal blasted at a frequency scientists had long considered a prime candidate for interstellar communication. The hydrogen line at 1420 MHz. And then, just as suddenly as it appeared, it vanished, never to be detected again. Decades later, we still don't know what caused it. The signal was narrowband, meaning it occupied a very specific slice of the radio spectrum, unlike the broad, messy emissions from natural celestial objects. It also matched predictions for how an artificial signal from deep space might appear. But here's the catch: if it was a message from an advanced civilization, why hasn't it repeated? Astronomers have scanned the same patch of sky near the constellation Sagittarius countless times, listening for another whisper. Silence. Some researchers argue it could have been a one-time cosmic fluke, like a comet's hydrogen cloud reflecting sunlight, though even that theory has holes. Others wonder if we simply missed the follow-up. What if the sender was transmitting in a direction we weren't listening? The WOW signal remains a tantalizing enigma, a brief cosmic shout that defies explanation. Whether it was aliens saying hello or nature playing a trick on us, one thing's certain: it's proof that the universe still has secrets we've only begun to uncover. While the WOW signal left us with unanswered questions, another cosmic mystery has been teasing astronomers with a pattern so strange it challenges everything we know about deep space transmissions. Enter FRB 121102, the first fast radio burst ever observed repeating its signal. Unlike the one-time blips we detected before, this one kept coming back, sending powerful pulses across the universe like a cosmic heartbeat. Discovered in 2012, this burst didn't just originate from any random corner of space. It came from a tiny, turbulent dwarf galaxy over 3 billion light-years away, a place where stars are born in chaotic bursts. What makes FRB 121102 so extraordinary is its rhythm. Most fast radio bursts are here and gone phenomena, but this one follows no predictable schedule, firing off intense radio waves in sporadic clusters. At its peak, it released more energy in a millisecond than our Sun does in 80 years. So what could possibly create such monstrous, repeating explosions? One leading theory points to magnetars, neutron stars with magnetic fields so strong they could strip the electrons from your body at 1,000 kilometers away. These cosmic powerhouses might unleash colossal flares, twisting magnetic fields until they snap, releasing those telltale radio bursts. But there's a twist. Some of the signals patterns don't quite fit the magnetar model, leading to more speculative ideas. Could it be something even more exotic? A handful of scientists have dared to propose that such precise, repeating bursts might hint at artificial origins, maybe an alien megastructure harnessing energy, or a beacon intentionally designed to cut through the cosmic noise. While that's a long shot, it's a reminder that when nature defies explanation, even the wildest theories deserve a glance. For now, FRB 121102 remains a dazzling enigma, proving that some cosmic mysteries don't just fade away. They keep knocking, waiting for us to unravel their secrets. While FRB 121102 teased us with its unpredictable bursts, another fast radio burst has left astronomers stunned for the exact opposite reason: its eerie clockwork precision. Meet FRB 180916, the cosmic metronome that pulses with a 16-day cycle so regular you could almost set your watch to it. Discovered in 2018, this signal follows a pattern unlike anything else we've observed in the universe. It blasts out radio waves for 4 straight days, then falls completely silent for 12, repeating the cycle over and over like some interstellar broadcast schedule. What makes this rhythm so baffling? For starters, most cosmic phenomena don't operate with such mechanical consistency. Stars flicker, black holes belch sporadically. Even pulsars, nature's most precise timekeepers, experience tiny hiccups. But FRB 180916 doesn't waver. Its 16-day cadence points to something far more structured, as if it's tied to an orbital dance or a rotating object with impeccable timing. The leading theory, a neutron star locked in a gravitational tango with another massive object, possibly a companion star or black hole. Here's how it might work. As the neutron star orbits, its powerful magnetic field interacts with stellar winds or debris from its partner, creating periodic bursts when conditions are just right. Picture a lighthouse beam sweeping past, except instead of light, it's a torrent of radio waves unleashed only during specific phases of its orbit. Some models suggest the 12-day silence could be the neutron star moving behind its companion, blocked from view, while the active phase happens when it swings back into the line of sight. But there's a twist. Not all the data fits neatly into this binary system idea. The signal's sheer power and the way its frequency changes over time have prompted alternative explanations, like a wobbling magnetar or even a cosmic collision zone where objects smash together at predictable intervals. And of course, the elephant in the room. Could such regularity hint at something more deliberate? While most scientists dismiss the idea of artificial origins, the precision of FRB 180916 forces us to ask deeper questions about how nature can mimic what feels almost engineered. For now, this 16-day enigma remains one of the universe's most tantalizing puzzles. It's a reminder that out there in the darkness, celestial objects might be moving to rhythms we've only just begun to hear. And each time this signal repeats, it's not just a burst of energy, it's a clue waiting to be deciphered. Long before astronomers knew about repeating fast radio bursts, there was one that started it all, the Oumuamua burst. Detected in 2007 while sifting through archived data from the Parkes radio telescope in Australia, this fleeting cosmic explosion rewrote the textbooks. Lasting just 5 milliseconds, it packed more energy than our sun emits in 30 years, a staggering outburst from somewhere deep in the universe's uncharted reaches. What made it so revolutionary at the time? Nothing like it had ever been seen before. The signal, officially dubbed FRB 010624, seemed to come from nowhere and vanish just as quickly, leaving astronomers with two burning questions. What could produce such an intense, brief flash of radio waves? And was this a freak cosmic accident, or were there more waiting to be found? The debate tore through the scientific community. Some argued it had to be a one-time cataclysm, perhaps a neutron star collapsing into a black hole or two superdense objects merging in a violent finale. Others suspected it might be the first glimpse of an entirely new class of phenomena, one that could be repeating if only we knew where and how to look. For years, the mystery deepened. The burst's origin point in the direction of the Magellanic Clouds offered no obvious clues. No known star, galaxy, or remnant matched the location, and attempts to find a repeating signal in the same region turned up empty. Skeptics even floated terrestrial explanations, maybe a glitch in the telescope, or a passing satellite reflecting stray radio waves back to Earth, but the data held up. This was real, and it was coming from deep space. Then, in 2013, everything changed. The discovery of FRB 121102, the first repeating fast radio burst, proved that these signals weren't all one-offs. Suddenly, the Lorimer burst wasn't just a bizarre outlier, it was the first breadcrumb in a trail of cosmic enigmas. Today, we know fast radio bursts are far more common than anyone imagined back in 2007. But the original mystery still lingers. Was the Lorimer burst truly a singular event, or is it out there somewhere, repeating on a timescale too long for us to have caught it again? What's undeniable is its legacy. That 5 millisecond blip opened an entirely new window into the universe's most extreme phenomena. It showed us that space is still full of surprises, and sometimes the biggest discoveries begin with the smallest, most fleeting signals. Among all the unexplained signals that have sparked debates about possible alien origins, few are as polarizing as SHB 02+14a. Picked up by the SETI at Home project in the early 2000s, this faint radio whisper from the direction of the constellation Pisces immediately stood out, not because it was powerful or repeating, but because it did something peculiar. It drifted in frequency. Now, why does that matter? Natural cosmic radio sources like pulsars or interstellar gas typically emit at fixed frequencies. But SHB 02+14 shifted slightly over time, as if the source were moving, or as some argued, as if it were coming from a planet orbiting a distant star. The signal appeared 3 times in the same patch of sky near Pisces, hovering around the hydrogen line frequency, that same magic number, 1420 MHz, that scientists speculate alien civilizations might use for communication. But here's where things get messy. The signal was incredibly weak, barely distinguishable from background noise, and it vanished as mysteriously as it appeared. Critics quickly pointed out that terrestrial interference, like a passing airplane or a malfunctioning microwave, could mimic those exact properties. Even the drift in frequency could be explained by something as mundane as a satellite's Doppler shift. And then there's the location. Pisces is a relatively quiet region of space, devoid of nearby stars or known exoplanets that could host advanced life. Yet the signal's defenders counter with a compelling point. If it was just interference, why did it show up multiple times in the same celestial coordinates? And why at a frequency so cosmically significant? The debate rages on, with some researchers calling it the most promising candidate for an extraterrestrial signal we've ever detected, while others dismiss it as a textbook case of wishful thinking. What makes SHB 02+14 so fascinating isn't just the science, it's the psychology. It forces us to confront how desperately we want to believe we're not alone, and how easy it is to project meaning onto the universe's random whispers. Whether it was aliens or just a glitch, this tiny, drifting signal reminds us that the line between discovery and delusion is thinner than we'd like to admit. And somewhere out there, in the void near Pisces, the truth still lingers just out of reach. In 1974, scientists aimed the Arecibo radio telescope at a star cluster 25,000 light-years away and beamed a carefully crafted message into the cosmos, a binary encoded greeting card for any intelligent life that might be listening. The transmission contained information about human DNA, our solar system, and even a stick figure of a person. Fast forward 27 years to 2001, and something astonishing appeared in a wheat field in England. A massive, intricate crop circle near the Chilbolton radio telescope bore an uncanny resemblance to the original Arecibo Message, but with eerie alterations. At first glance, the formation mirrored the same grid-like structure of the 1974 transmission, but upon closer inspection, key details had changed. The human stick figure was replaced by a larger, bulbous-headed silhouette, the classic grey alien shape. The double helix of DNA was rearranged, and the depiction of our solar system now emphasized not just Earth, but 3 other planets, with the third one conspicuously enlarged. The most unsettling tweak, the sender's identity at the bottom had transformed from the Arecibo telescope's dish to what looked like an alien face. So was this a cosmic reply, a clever hoax, or something even stranger? Skeptics pointed out that crop circles, no matter how complex, are easily created by humans with simple tools. The Chilbolton Formation appeared near a well-known scientific facility, making it a prime target for pranksters. And the timing, just before the harvest season when crop circles peak, seemed suspiciously convenient. Yet the precision of the design raised eyebrows. The grid contained exactly 1,679 squares, just like the original message, a number chosen because it's the product of 2 prime numbers, a mathematical hint that the message was meant to be decoded. Then there's the matter of the changes themselves. The altered DNA structure didn't just look random. It featured an extra strand, a detail that some researchers argue could theoretically make genetic material more stable. And the emphasized planets in the solar system. One matches the position of a then recently discovered exoplanet, a detail the original Arecibo Message couldn't have included. The debate still simmers. Was this an elaborate art project, a collective hallucination, or the closest thing we've ever gotten to a cosmic pen pal? Whether human hands or something far more extraordinary carved those stalks, the Chilbolton Formation remains a haunting echo of our own message to the stars, one that blurs the line between earthly mischief and the tantalizing possibility that someone or something might finally be talking back. The mystery began on a quiet night in 2015, when Russian astronomers scanning the skies with the Ratan 600 radio telescope caught something unexpected. A strong, narrowband signal emanating from the direction of HD 164595, a star almost identical to our Sun, located 94 light-years away in the constellation Hercules. What made this detection so electrifying was the signal's characteristics: a sharp spike at 11 GHz, a frequency with no known natural cosmic source, and a pattern that seemed too precise to ignore. For a brief moment, the scientific world held its breath. Here was a sun-like star, the type we'd expect to host planets, emitting a signal that matched theoretical predictions for an artificial transmission, perhaps a deliberate broadcast or even leakage from an advanced civilization's technology. The star had already made headlines the previous year when astronomers discovered it harbored at least one Neptune-sized planet, though that world orbited too close to be habitable. Could there be others in the system, hidden from our view, where intelligence might thrive? But as quickly as the excitement flared, reality set in. When other telescopes tried to confirm the signal, they found nothing. No repeat, no trace. The search for a mundane explanation began, and the leading culprit soon emerged: human interference. 11 gigahertz is a frequency used by military satellites and earthly radar systems, and the signal's properties aligned suspiciously well with a passing satellite or aircraft emission reflecting off the telescope's dish. Even the timing pointed to something terrestrial. The signal appeared when the telescope was pointed toward the horizon, where earthly radio noise is most likely to creep in. Yet the story doesn't end there. What makes HD 164595 signal so compelling isn't just the false alarm. It's the lesson it taught us about the hunt for extraterrestrial intelligence. For decades, SETI researchers have wrestled with the needle in a haystack problem, distinguishing genuine cosmic signals from the ever-growing sea of human-made radio pollution. Satellites, Wi-Fi, even microwave ovens can mimic the narrowband transmissions we'd expect from aliens. The HD 164595 incident became a case study in caution, a reminder that extraordinary claims require not just detection, but verification from multiple independent sources. Still, some lingering questions remain. Why did the signal appear so strongly in one observation and then vanish completely? And what if, just what if, it wasn't interference at all, but a one-time burst from a civilization that briefly flickered onto our radar before disappearing back into the cosmic dark? While the evidence leans heavily toward a terrestrial explanation, HD 164595's fleeting whisper stands as a testament to both the promise and the pitfalls of listening for voices in the stars. It's a reminder that every signal, no matter how tantalizing, must survive the gauntlet of skepticism before it can rewrite our understanding of the universe. And sometimes the most profound discoveries aren't the ones we make, but the ones we almost did. If fast radio bursts were puzzle pieces, FRB 190523 would be the one that doesn't quite fit the picture. Most of these cosmic flashes originate in tiny, chaotic dwarf galaxies, places where stars are born in frenzied bursts, and conditions are ripe for explosive phenomena. But in 2019, astronomers tracing the origin of FRB 190523 found something unexpected. It came from a massive, sedate spiral galaxy nearly 8 billion light-years away, a quiet giant completely unlike the turbulent nurseries we'd associated with these bursts before. This wasn't just a minor detail, it was a revelation. If the same phenomenon could arise in such drastically different environments, it meant our theories about what causes fast radio bursts needed a serious rethink. Until then, the leading explanation for repeating FRBs like 121102 involved magnetars, the ultramagnetic corpses of dead stars often found in young, active galaxies. But a calm, mature galaxy like this one, magnetars here would be ancient. Their magnetic fields faded over time, hardly the powerhouse needed to generate such violent bursts. So what could lurk in this quiet cosmic neighborhood capable of unleashing FRB 190523's staggering energy? One possibility points to colliding neutron stars, cataclysmic mergers that might occur even in older galaxies. Another theory suggests active supermassive black holes, their gravitational whirlpools accelerating particles to extreme speeds, though no such black hole was detected in the burst's vicinity. Then there's the wild card. What if some fast radio bursts aren't caused by one single thing, but multiple cosmic engines working in different corners of the universe? The implications are profound. If FRBs can spring from both dwarf galaxies and massive spirals, it suggests the universe has more than one way to create these brilliant flashes. Maybe magnetars dominate in young galaxies, while collisions or black hole interactions take over elsewhere. Or perhaps we're glimpsing an entirely new class of high-energy physics, where conditions we don't yet understand can trigger these bursts anywhere. What's certain is that FRB 190523 shattered the mold. It forced astronomers to widen their search, to consider that the cosmos might be hiding multiple keys to the same mystery. And as we keep listening, each new signal, whether from a raucous dwarf galaxy or a serene spiral, brings us closer to understanding just how many voices the universe uses to speak. Out in the constellation Cygnus, about 1,500 light-years from Earth, there's a star that refuses to play by the rules. KIC 8462852, better known as Tabby's star, has baffled astronomers since 2015 with its bizarre, unpredictable flickering. Unlike most stars, which dim in regular, gentle rhythms caused by orbiting planets, this one plunges into darkness erratically, sometimes dropping in brightness by a staggering 22%, as if something colossal is passing in front of it. And just as mysteriously, it brightens again with no discernible pattern. The strangeness began when data from NASA's Kepler Space Telescope revealed these irregular dips in the star's light. Planets, even giant ones, typically block less than 1% of a star's light when they transit, but Tabby's star's fluctuations were off the charts. One early theory sent shockwaves through the scientific community and the public imagination. Could this be evidence of an alien megastructure, specifically a Dyson swarm, a hypothetical array of solar collectors built by an advanced civilization to harness their star's energy? The idea wasn't entirely far-fetched. After all, if a civilization grew powerful enough, capturing stellar energy on a massive scale would be the next logical step. And the star's erratic dimming matched what such a structure might look like from afar, uneven, patchy, and irregular as panels moved in and out of view. But science thrives on skepticism, and alternative explanations soon emerged. One leading natural theory involves swarms of comets, not just a few, but hundreds of thousands, maybe even millions, orbiting the star in a chaotic cloud. If these icy bodies trailed vast plumes of dust and debris, they could block light unevenly as they passed between the star and Earth. Another idea points to interstellar dust, not from comets but from some cataclysmic event in the star's past, a collision of planets perhaps, leaving behind a sprawling disk of fragments that still haunts the system. Then there's the star itself. Tabby's star is slightly larger and hotter than our Sun, and some researchers argue its own behavior might explain the dimming. Stars with intense magnetic activity can develop dark spots far larger than our Sun's, and if Tabby's star is prone to extreme stellar storms, those spots could account for some of the light fluctuations. Yet even this doesn't fully explain the deepest, most dramatic dips. The truth is, we're still piecing this puzzle together. Every new observation adds layers to the mystery. In 2017, the star dimmed again, and astronomers worldwide scrambled to point telescopes at it, capturing data across every wavelength from radio to X-ray. The results: no telltale signs of artificial structures, no laser-like radio signals, no excess heat that would suggest megascale engineering. But the natural explanations aren't perfectly tidy either. The comet swarm theory requires an implausibly huge number of comets, and the dust hypothesis struggles to explain why the debris hasn't dispersed over time. What makes Tabby's star so captivating isn't just the science, it's what it represents. It's a reminder that the universe is weirder than we imagine, that even the most outlandish ideas deserve consideration until the evidence rules them out. Whether it's comets, dust, star spots, or something beyond our current understanding, this star challenges us to keep looking, questioning, and wondering. And until we crack its code, it stands as a humbling testament to all we have yet to learn. In late 2020, a team of astronomers working with the Breakthrough Listen project detected something extraordinary: a narrowband radio signal clocking in at 982 MHz emanating from Proxima Centauri, the closest star system to our own. Dubbed BLC-1, the signal sent ripples of excitement through the scientific community. Here was a transmission that ticked all the boxes for potential artificiality. It was narrowly focused in frequency, drifted in a way consistent with a planet's movement, and originated from the very system where we'd already discovered 2 exoplanets, one of which sits in the habitable zone. For a moment, it felt like the discovery of the century. Proxima Centauri b, that potentially rocky, Earth-sized world, suddenly seemed a little less lonely. The signal's properties were undeniably intriguing. Unlike the messy broad-spectrum noise of natural cosmic phenomena, BLC-1 was clean and precise, exactly the kind of fingerprint we'd expect from a technological source. Even more compelling, the frequency it occupied was unusually quiet, a part of the radio spectrum mostly free from the chatter of human-made interference. It was as if the universe had handed us a perfectly wrapped gift, one that whispered, "This might be it." But science thrives on skepticism, and the closer researchers looked, the more the story unraveled. The first red flag came when follow-up observations failed to detect the signal again. If this was a deliberate broadcast from Proxima Centauri, why wouldn't it repeat? Then came the deeper analysis. While the signal's drift matched what we'd expect from a planet, it also aligned suspiciously well with the behavior of human technology, specifically oscillators found in everyday electronics like computers and smartphones. The nail in the coffin, further scrutiny revealed that BLC-1's frequency overlapped with known sources of terrestrial interference, likely a stray radio emission from a passing satellite or even a malfunctioning device somewhere on Earth. What makes BLC-1 so fascinating isn't just the false alarm, it's the lesson it taught us about the needle in a haystack challenge of SETI research. Even in the quietest corners of the radio spectrum, human-made noise creeps in, masquerading as the very signals we're desperate to find. The Proxima Centauri incident highlighted how even the most promising detections demand relentless verification, a gauntlet of tests to weed out wishful thinking. Yet, in a strange way, BLC-1 also gave us hope. If our instruments are sensitive enough to catch whispers this faint, then one day when the right signal comes along, we might just be ready to hear it. Until then, it stands as a humbling reminder that the universe loves to tease us, offering glimpses of answers while keeping its biggest secrets just out of reach. For years, fast radio bursts were cosmic mysteries with no clear origin, until FRB 200428 changed everything. This wasn't just another blip from the distant universe, it was a galactic neighbor, erupting from a known magneta right in our own Milky Way. On April 28, 2020, astronomers watched as SGR 1935+2154, a highly magnetic neutron star just 30,000 light-years away, unleashed a millisecond burst of radio waves so powerful it echoed across observatories worldwide. What made this detection earth-shattering? For the first time, we could trace an FRB directly to its source, linking these enigmatic signals to the violent tantrums of magnetas. The clues had been piling up for years. Magnetas, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, were always prime suspects. Their explosive flares, known as starquakes, can rip open their surfaces, releasing energy equivalent to 1 billion suns. But until FRB 200428, no one had caught a magneta in the act of producing both an X-ray flare and a fast radio burst simultaneously. That day, NASA Neil Gehrels Swift Observatory spotted the magneta's X-ray eruption, while the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, snagged the accompanying radio burst. The timing was impeccable. The two events were separated by just milliseconds, a smoking gun linking magneta activity to FRBs. Yet even with this breakthrough, the puzzle isn't completely solved. Why do some magneta flares produce FRBs while others don't? The answer might lie in the star's magnetic field lines. When these lines twist and snap, they could accelerate particles to near light speeds, generating shockwaves that emit both X-rays and radio waves. But here's the catch: FRB 200428 was weaker than most extragalactic bursts. That suggests magnetas in distant galaxies, unleashing even more energetic flares, might be responsible for the louder FRBs we've detected. The implications ripple far beyond this one signal. If magnetars can produce FRBs, it means these cosmic flashes might not all come from the same sources. Some could be magnetars in their youth, others in their death throes, or even exotic variants we haven't discovered yet. It's a reminder that the universe rarely hands us simple answers. Instead, it offers clues, each one pulling back another layer of the cosmic curtain. And with every magnetar flare we catch, we're one step closer to decoding the language of these interstellar sirens. The year was 1967, and inside a modest radio astronomy lab at the University of Cambridge, a young graduate student named Jocelyn Bell Burnell was poring over reams of paper chart recordings from a new telescope she'd helped build. Then she saw it, a series of sharp, rhythmic pulses arriving every 1.337 seconds, so precise they seemed almost mechanical. At first, the team jokingly labeled the signal LGM-1, short for Little Green Men. It was an unspoken thought hovering in the air like static. Had they just stumbled upon a beacon from an alien civilization? The pulses weren't random noise or interference. They arrived with clockwork regularity, each burst lasting just milliseconds, as if some cosmic entity were tapping out a message. The team kept the discovery quiet, wrestling with the implications. If this was artificial, acknowledging it publicly could spark panic, or worse, false hope. But as more of these signals popped up across the sky, a pattern emerged. They weren't messages, they were something entirely new. The truth, when it finally clicked, was even more extraordinary. They'd discovered pulsars, the rapidly spinning corpses of massive stars, lighthouses of the cosmos beaming radiation into the void with every rotation. What made pulsars so revolutionary wasn't just their eerie precision. They were the first concrete evidence of neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons. These cosmic remnants were theoretical ghosts until Bell Burnell's LGM signal brought them into sharp focus. Suddenly, astrophysics had a new tool. Pulsars became cosmic clocks, their unwavering ticks helping scientists test Einstein's theory of relativity, map the Milky Way's magnetic fields, even hunt for gravitational waves. Yet the story carries a bittersweet edge. While Bell Burnell's supervisor, Anthony Hewish, later shared the Nobel Prize for the discovery, Bell herself was controversially excluded, a decision that still sparks debate about recognition in science. But her legacy transcends awards. That initial moment of wonder, the thrill of thinking they'd found aliens, underscores how often the universe surprises us. The LGM signal wasn't proof of extraterrestrial intelligence, but it was proof of something equally profound. Nature's ability to mimic our wildest imaginings, then reveal truths far stranger than fiction. Today, pulsars are more than celestial curiosities. They're guideposts for interstellar navigation, natural laboratories for extreme physics, and reminders that sometimes the greatest discoveries begin with a question we're almost afraid to ask. And tucked into their history is that fleeting, exhilarating possibility. For a few weeks in 1967, humanity dared to believe we might not be alone in the universe. Even in being wrong, we stumbled upon a wonder that reshaped our understanding of the stars. Tabby's star, or KIC 8462852, didn't just challenge our understanding of cosmic signals, it rewrote the rules entirely. When astronomers first noticed its strange, erratic dimming patterns back in 2015, the immediate assumption was planets. But this wasn't the gentle, rhythmic dipping caused by an orbiting world. It was more like the star was being swallowed by something massive and irregular. At times, its light would drop by a jaw, dropping 22%, far more than even a Jupiter-sized planet could block. The dips didn't follow any predictable schedule either, appearing and vanishing without warning, as if some unseen force were flickering a cosmic dimmer switch. For a while, the most sensational explanation, an alien megastructure, captured imaginations worldwide. The idea wasn't pure fantasy. A Dyson swarm, a hypothetical network of energy-collecting satellites built by an advanced civilization, could theoretically cause such irregular shadows. If a civilization had harnessed their star's power on a massive scale, the uneven distribution of these structures might explain the bizarre light patterns. Even the star's slight but measurable long-term dimming discovered in later studies seemed to fit. Over a century of historical data showed Tabby's star had gradually grown darker, as if something were slowly accumulating around it. But science demands more than tantalizing speculation. As researchers dug deeper, alternative theories emerged, some almost as strange as the alien hypothesis. One leading explanation involves colossal swarms of comets, not just a few dozen, but hundreds of thousands, maybe even millions, orbiting in a chaotic storm. If these icy bodies trailed enormous plumes of dust, their erratic orbits could block light in unpredictable clumps. Another theory points to leftover debris from a planetary collision, a cosmic catastrophe that left behind a sprawling, uneven disk of fragments. Then came a breakthrough in 2018. Detailed observations from the Hubble and Keck telescopes revealed something crucial. The dimming wasn't uniform across all wavelengths. When Tabby's star faded, its blue light dimmed more sharply than its red light. A fingerprint of fine dust particles, not solid megastructures. Dust scatters blue light more easily, a phenomenon familiar to anyone who's watched a sunset. This discovery tilted the scales toward natural explanations, though it didn't fully solve the mystery. Where did all this dust come from, and why hasn't it dispersed over time? The latest research suggests an even wilder possibility: a devoured planet. Some astronomers speculate that Tabby's star might have violently torn apart a nearby world, its gravitational forces ripping the planet into shreds. The resulting debris, now trapped in a lopsided orbit, could create those irregular shadows as it drifts between the star and Earth. It's a grim but compelling scenario, one that mirrors the chaotic early days of our own solar system, when planetary bodies often collided or were torn asunder. Yet even now, Tabby's star refuses to surrender all its secrets. The dust theory explains much, but not everything, like the century-long dimming trend which still lacks a perfect natural analog. Some researchers argue we might be seeing multiple phenomena at once: dust clouds, comet swarms, and the star's own volatile behavior conspiring to create this cosmic hall of mirrors. What makes Tabby's star so endlessly fascinating isn't just the science, it's the way it forces us to confront the limits of our knowledge. Here's an object that, at first glance, seemed to defy every known law of stellar behavior. It prompted us to consider possibilities from the mundane to the extraordinary, from comet storms to alien engineering. And while the dust explanation now seems most likely, that initial moment of uncertainty, that thrilling "what if?" remains a testament to how much we still have to learn about the universe. Every flicker of this enigmatic star is a reminder. Sometimes the cosmos saves its strangest performances for the most unassuming actors. Just when we thought we had fast radio bursts figured out, along came FRB 20200120E to turn everything upside down. Discovered in January 2021, this signal didn't come from a rowdy dwarf galaxy or a turbulent star-forming region like most of its cosmic cousins. Instead, it pulsed from somewhere utterly unexpected, a serene, ancient globular cluster nestled in the nearby galaxy M81, roughly 12 million light-years away. Globular clusters are cosmic retirement homes packed with stars billions of years older than our Sun. They're quiet, stable places where stellar fireworks are rare. So why would an FRB, a phenomenon we'd associated with young, violent environments, suddenly pop up in a place like this? It's like finding a screaming jet engine in a library. The discovery sent astronomers scrambling to rethink their playbooks, because if FRBs can emerge from such tranquil neighborhoods, our understanding of what creates them might be missing a crucial piece. The leading suspect this time, a zombie star refusing to die quietly, specifically a highly magnetized neutron star, a magnetar, that somehow found itself in this aging stellar community. But here's the twist: magnetars are typically born from the explosive deaths of massive, short-lived stars. Globular clusters with their ancient populations shouldn't have many of these young stellar remnants left. That leaves two possibilities, each more intriguing than the last. Either this magnetar is a rare straggler from a long-ago supernova, preserved in the cluster's gravitational embrace, or it's the product of two older stars colliding or merging, reigniting the fires of youth in a spectacular second act. The implications are staggering. If collisions can spawn magnetars capable of producing FRBs, it means these bursts might not be exclusive to the universe's chaotic nurseries. They could happen anywhere, even in the quietest corners of space, where stars have drifted peacefully for eons. It also raises tantalizing questions about how many magnetars might be hiding in plain sight, disguised by their serene surroundings. But FRB 202000120E isn't done surprising us. Unlike many FRBs that blast their energy across vast cosmic distances, this one was relatively close enough, in fact, to detect something unusual: faint, lower-frequency radio waves trailing the main burst. That's a clue, like finding smoke lingering after a firework explodes, hinting at the physics behind the blast. Some researchers think this afterglow could come from shock waves rippling through debris around the magnetar, or even from a companion star's atmosphere being violently stirred by the explosion. What makes this signal so extraordinary isn't just its unlikely address, it's the way it forces us to widen the search. If FRBs can ignite in places we never thought to look, how many more are we missing? And if ancient globular clusters can harbor such energetic outliers, what other cosmic elders might be hiding secrets beneath their quiet facades? Every time we think we've mapped the boundaries of the possible, the universe throws us a curveball, and FRB 202000120E might just be the most thrilling pitch yet. There's something unsettling about the idea that everything we see in the universe, every star, every galaxy, every cosmic structure, might be caught in a silent, invisible current, pulled toward some unseen force beyond the edges of our reality. Yet that's precisely what astronomers stumbled upon when they discovered the dark flow, an eerie, unexplained movement of galaxy clusters racing in the same direction at blistering speeds, as if drawn by a cosmic magnet we can't locate. This isn't just a slight drift. These clusters are hurtling at over 2 million miles per hour toward a single patch of space near the constellations Centaurus and Vela, a motion that defies all known gravitational logic. Here's the problem. According to our current understanding, the universe's large-scale structure should distribute mass evenly enough that no single direction would exert such a pull. The Big Bang's afterglow, the cosmic microwave background, should be the only reference frame for motion, yet these galaxies are ignoring the rules, streaming towards something outside the observable universe. So what's tugging them? One theory ventures into the realm of parallel universes. If our cosmos is just one bubble in a vast multiverse, neighboring universes might exert gravitational influence beyond the horizon of our own, creating this mysterious flow. It's a dizzying thought that we're sensing the gravitational shadow of another reality, a place where the laws of physics might be utterly alien. Then there's the even more unsettling possibility, a colossal, unimaginably dense structure lurking in the unobservable void. Picture a supercluster of galaxies so massive its gravity warps space-time across cosmic distances, or a remnant fragment from a previous universe's collapse lingering like a ghost in the darkness. The catch: we'll never see it directly. By definition, anything beyond the observable universe's edge is forever hidden from our view, its light unable to reach us in the finite age of the cosmos. But the dark flow's existence is hotly debated. Some researchers argue it could be an artifact of incomplete data or measurement biases, while others point to peculiarities in the cosmic microwave background that might mimic the effect. Yet multiple studies, including analyses from NASA's Wilkinson Microwave Anisotropy Probe and the Planck satellite, have detected the same eerie motion, deepening the mystery. Whether it's proof of the multiverse, a relic of a long-vanished epoch, or just a cosmic illusion, the dark flow forces us to confront how little we understand about the universe's true scale. It's a humbling reminder that even the grandest structures we've mapped might just be leaves on a river swept along by currents we're only beginning to sense. And somewhere beyond the edge of everything we know, the universe might be whispering secrets we're not yet equipped to hear. Rising from the heart of the Milky Way like twin cosmic geysers, the Fermi Bubbles stretch 25,000 light-years above and below our galaxy's disk, colossal structures glowing with high-energy gamma rays. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these gargantuan formations remain one of the most puzzling features in our galactic backyard. What's shocking isn't just their size enough to engulf half the visible sky if we could see them with the naked eye, but the sheer intensity of their radiation, blazing with energies 100 billion times greater than visible light. For over a decade, astronomers have wrestled with the question, what could possibly create such enormous, symmetrical bubbles of pure gamma radiation? The prime suspect sits at the very center of the galaxy Sagittarius, a star, the supermassive black hole anchoring the Milky Way. One leading theory suggests that 6 million years ago, Sagittarius, a star, staged a violent feast, devouring an enormous clump of gas and dust. The resulting energy could have launched jets of superheated plasma shooting outward at near light speed, inflating these bubbles like cosmic balloons. The gamma rays we see today might be the afterglow of that ancient cataclysm, the shock waves from that meal still reverberating through intergalactic space. But not everyone's convinced. Alternative explanations point to something even more exotic: dark matter. If these invisible particles collide and annihilate near the galaxy's core, they could release bursts of gamma radiation, slowly building the Fermi bubbles over eons. It's a tantalizing idea, offering indirect evidence for the universe's most elusive substance. Yet critics argue the bubble's sharp edges and symmetrical shape don't quite match predictions for dark matter decay, which should produce a more diffuse, uneven glow. Then there's the wild card, a starburst frenzy. Some models suggest that around the same time the bubbles formed, the Milky Way's core experienced a frenetic wave of star formation. These short-lived, massive stars would have died in spectacular supernova, their combined explosions pumping enough energy into the galactic center to blow the Fermi bubbles into existence. It's a cosmic tug-of-war between competing explanations, with each camp marshalling evidence from gamma-ray spectra, simulations, and observations of other galaxies. What makes these bubbles so fascinating is their sheer persistence. Unlike fleeting fast radio bursts or one-off signals, the Fermi bubbles are a permanent fixture in our sky, a reminder that the universe's greatest mysteries aren't always light years away. Sometimes they're right above us, hidden in plain sight, waiting for us to piece together their explosive origin story. Whether born from a black hole's tantrum, dark matter's whispers, or the death cries of ancient stars, one thing's clear: our galaxy has a dramatic past, and these bubbles are its lingering echo. Deep in the heart of distant galaxy clusters, astronomers have stumbled upon a whisper that might just be the first tangible clue to dark matter's existence. A faint but persistent X-ray signal at 3.5 kilo-electron volts or keV. This isn't some random cosmic static. It's an emission line that glows with eerie consistency across multiple clusters, as if something unseen is quietly broadcasting its presence. The implications are staggering. If this signal truly comes from dark matter, It would be the first direct evidence of the universe's most elusive substance, the invisible scaffolding that holds galaxies together yet has evaded detection for decades. The story begins with observations of the Perseus cluster, a massive gathering of galaxies swimming in a sea of superheated gas. In 2014, researchers noticed an odd spike in X-ray emissions at an energy level that didn't match any known atomic transition. Normally, such lines come from specific elements like iron or oxygen, but 3.5 keV had no obvious chemical fingerprint. That absence is what made it so tantalizing. If it wasn't ordinary matter producing this glow, could it be dark matter particles annihilating or decaying in the void between galaxies? The leading candidate is a hypothetical particle called the sterile neutrino, a ghostly cousin to the neutrinos we know, but far heavier and even less interactive with normal matter. If sterile neutrinos exist, their decay could produce X-rays at precisely this energy, leaving behind the 3.5 keV line as a calling card. It's a perfect fit on paper. Dark matter should cluster in galaxy halos, and these X-rays appear strongest in the densest regions of clusters, right where theory predicts the signal should be. But the universe rarely serves up easy answers. Skeptics point to alternative explanations, like plasma physics quirks or exotic sulfur ions emitting X-rays in ways we don't fully understand. Even more confounding, the signal isn't always there. Some observations, like those of the Milky Way center, another place teeming with dark matter, show no trace of the 3.5 keV line. If dark matter is universal, why wouldn't it show up everywhere we look? The debate rages on, with new studies adding twists to the plot. In 2020, researchers analyzing data from NASA's Chandra X-ray Observatory and ESA's XMM Newton found the signal in stacked observations of galaxy clusters, bolstering the dark matter case. Yet others argue that calibration errors or instrumental noise could mimic the line, casting doubt on its extraterrestrial origins. It's a classic cosmic tug of war. One side sees a breakthrough, the other sees a mirage. What makes this search so electrifying isn't just the science, it's the stakes. If the 3.5 keV line is confirmed as dark matter's signature, it would crack open one of physics' greatest mysteries, revealing the hidden architecture of the cosmos. If not, it's still a masterclass in how science grapples with the unknown, sifting through noise for whispers of truth. Either way, this faint X-ray glow reminds us that sometimes the universe's biggest secrets hide in the smallest details, waiting for us to decode them. In October 2017, astronomers spotted something streaking through our solar system that didn't belong. A strange, tumbling object unlike anything we'd ever seen before. Named Oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed visitor from interstellar space. But what made this cosmic interloper truly baffling wasn't just its origin, it was the way it moved. Instead of following a predictable path shaped by gravity alone, Oumuamua sped up slightly as it raced away from the sun, as if pushed by an invisible force. At first glance, the explanation seemed straightforward. Comets often accelerate like this due to outgassing when sunlight vaporizes their icy surfaces, releasing jets of gas that act like tiny thrusters. But Oumuamua had a problem: no visible tail. Telescopes scoured the object for signs of water vapor, carbon dioxide, or other common comet ingredients, yet found nothing. If it wasn't outgassing, what was nudging it forward? One theory suggests Oumuamua might have been a cosmic iceberg made of molecular hydrogen, a substance so light that even a small amount of vaporization could produce acceleration without leaving a detectable trail. Picture an ice cube quietly steaming away in the vacuum of space, its vanishing mass giving it just enough kick to defy expectations. The idea is intriguing, but there's a catch. Hydrogen ice is notoriously unstable, especially in the warmth of the inner solar system. Could such an exotic object survive long enough to reach us? Then there's the more provocative possibility that Oumuamua wasn't a natural object at all. Harvard astronomer Avi Loeb famously floated the idea that its acceleration and unusual shape, possibly flat and elongated, like a pancake, might hint at artificial origins. Could it be a discarded piece of alien technology, a solar sail riding the pressure of starlight? The notion captured headlines, but many scientists pushed back, arguing that extraordinary claims require extraordinary evidence. After all, nature is full of surprises, and jumping to extraterrestrial explanations risks overlooking simpler, undiscovered phenomena. The truth is, Oumuamua's brief visit left us with more questions than answers. By the time we noticed it, the object was already speeding away, too distant for follow-up observations. We'll never know for sure what it was, whether a hydrogen iceberg, a shattered fragment of a distant planet, or something even harder to explain. But its legacy endures as a humbling reminder of how much we still don't understand about the cosmos. Sometimes the most profound mysteries aren't signals from the void, but silent travelers passing through, leaving us to wonder what else might be out there, just beyond our grasp. Among the countless stars that dot our galaxy, a handful stand out for their bizarre infrared glow, so extreme that scientists have debated whether we might be glimpsing something never before seen in nature. These so-called Dyson Sphere candidates are stars wrapped in shrouds of heat, radiating the unmistakable signature of energy being absorbed and re-emitted on a mind-boggling scale. The concept traces back to physicist Freeman Dyson's radical idea in 1960. If an advanced civilization wanted to harness every drop of their sun's power, they might envelop it in a vast swarm of energy-collecting satellites, creating a structure so colossal it would glow faintly in infrared light as waste heat leaked into space. One of the most famous candidates is KIC 8462852, better known as Tabby's star. While its erratic dimming initially stole headlines, follow-up studies revealed another oddity, an excess of infrared radiation. Could this be the thermal fingerprint of alien engineering, the waste heat from a partially completed Dyson swarm, or is there a simpler explanation? The leading natural theory involves colossal clouds of dust, possibly from pulverized comets or a catastrophic planetary collision, absorbing starlight and re-radiating it as infrared. But even this explanation strains plausibility, requiring an almost unimaginable amount of debris to match the observations. Then there's TYC 612177161, a star whose infrared excess is so extreme it defies most natural models. Observations suggest something is blocking nearly 40% of its visible light while glowing fiercely in infrared, a disparity that's hard to square with known astrophysical processes. Some researchers argue this could be a Dyson sphere under construction, its patchwork of collectors casting uneven shadows. Others propose a more exotic natural scenario, a young star surrounded by a warped, misaligned disk of planet-forming material, bent into strange geometries by gravitational tugs from unseen worlds. But the plot thickens with objects like EPIC 244893984, a star that not only dims erratically but also shows infrared spikes consistent with temperatures expected from artificial megastructures. Detailed analysis revealed these spikes align with moments when the star's visible light drops sharply, as if something vast and hot is passing in front of it. Yet skeptics counter that similar patterns could arise from extreme stellar activity, giant sunspots or hyperactive magnetic loops heating localized patches of the star's atmosphere. What makes these candidates so compelling and so controversial is the tension between two possibilities. On one hand, they could be windows into cosmic engineering on a scale beyond human comprehension. On the other, they might simply be teaching us about previously unknown astrophysical phenomena like ultra-dense debris disks or hyper-efficient dust traps. The search for Dyson spheres isn't just a hunt for alien civilizations. It's a stress test for our understanding of how stars and planetary systems behave at the extremes. For now, the verdict remains open. Each new observation peels back another layer of the mystery, revealing just how much we still don't know about the universe's capacity for both natural wonders and perhaps artificial ones. Whether these infrared anomalies are alien megaprojects or celestial oddities, they remind us that the cosmos is stranger and more creative than we've yet imagined. For decades, rumors have swirled about an ancient alien satellite silently orbiting Earth, a shadowy object dubbed the Black Knight, said to have been watching over our planet for 13,000 years. Stories claim this mysterious craft was first detected by Nikola Tesla in the late 1800s, later spotted by military radar in the 1950s, and even photographed by NASA astronauts. But here's where fact and conspiracy collide like asteroids in the void. The truth begins with a mundane explanation: space debris. In 1960, the U.S. Discoverer 5 satellite lost its dark, heat-resistant outer casing, a jagged piece of insulation that tumbled into an unstable orbit. When radar picked it up years later, Cold War paranoia and sensational tabloids spun it into something far grander: an extraterrestrial probe. The myth snowballed, fueled by grainy images from early space missions that showed nothing more than discarded thermal blankets or detached spacecraft panels. Even Tesla's so-called detection, a misinterpretation of his experiments with radio waves bouncing off the ionosphere, not signals from an alien observer. But the Black Knight legend doesn't just thrive on misidentified junk. It taps into something deeper: our collective fascination with the idea that we're not alone, and that evidence of our cosmic neighbors might be hiding in plain sight. The human brain is wired to find patterns even where none exist. A fleck of dust on a camera lens becomes a UFO. A distant star's flicker morphs into an alien megastructure. The Black Knight thrives in that psychological sweet spot where mystery feels more thrilling than the truth. Yet the story takes an ironic turn. In recent years, actual unidentified objects like the tumbling upper stages of old rockets or the enigmatic A10BMLZ bag-sized debris spotted in 2019 continue to spark fresh speculation. The cycle repeats: a strange blip appears, the internet ignites, and another Black Knight is born. What's striking isn't just how often these myths resurface, but how they reflect our timeless urge to project wonder onto the cold, mechanical reality of spaceflight. So is the Black Knight pure fiction? Mostly. But its legacy is real, a testament to how easily the cosmos can become a canvas for our wildest stories. And in a universe brimming with genuine mysteries, that might be the most human thing of all. Some galaxies don't just glow quietly in the darkness, they explode outward in vast, chaotic sprays of radio waves, forming shapes so strange they look almost intentional. Among the most puzzling are the X-shaped radio galaxies, whose twin jets of high-energy particles don't shoot out in straight lines but instead curve dramatically, forming a colossal cosmic X visible across millions of light years. These aren't just pretty patterns, they're violent fingerprints of some of the most extreme physics in the universe, and they might hold clues to one of astronomy's biggest mysteries: what happens when supermassive black holes collide. Take NGC 326, for example. This galaxy's radio lobes stretch over 2.5 million light-years, twisting into an unmistakable X shape. At first glance, it defies logic. Supermassive black holes typically launch jets in opposite directions, like water from a spinning sprinkler. So why would they suddenly bend into such an elaborate structure? One leading theory points to a cataclysmic merger. Picture two black holes, each billions of times the mass of our Sun, spiraling toward each other in a gravitational dance. As they finally merge, their combined spin axis might flip like a wobbling top, redirecting their jets mid-eruption and leaving behind this twisted X-shaped scar. But there's another possibility: galactic indigestion. Sometimes, when a black hole feeds too greedily on surrounding gas, the influx can become unstable, causing its accretion disk to tilt wildly. This sudden shift could reorient the jets, sending them spiraling into new directions without requiring a collision at all. Simulations show that such chaotic feeding frenzies might produce X-shaped remnants as the black hole's outbursts flicker and pivot over millennia. What makes these galaxies so fascinating isn't just their strange shapes, it's the timeline they reveal. The outer lobes of the X are often fainter and more diffuse, suggesting they're relics of an older eruption, while the inner jets shine brighter, evidence of recent activity. It's like finding a fossilized footprint layered beneath a fresh one, showing how the galaxy's central engine has changed over time. And in some cases, like with the galaxy PKS 2014-55, the X isn't symmetrical at all. One arm might be bent more sharply than the other, hinting at external forces like intergalactic winds or gravitational tugs from neighboring galaxies warping the jets mid-flight. The implications stretch far beyond these celestial oddities. If X-shaped galaxies are indeed the aftermath of black hole mergers, they could help us understand how these monstrous objects grow so large. Each X might mark a violent chapter in a galaxy's life, a moment when two giants became one and reshaped their entire universe in the process, even more intriguing. Some astronomers suggest these bent jets could be sources of the mysterious ultra-high-energy cosmic rays that occasionally slam into Earth's atmosphere, particles carrying energies no human-made accelerator can match. Yet for all their grandeur, X-shaped radio galaxies raise as many questions as they answer. Why do some merging black holes create these perfect X's while others produce chaotic, tangled messes? Could the surrounding environment, like the density of gas in a galaxy's core, determine whether the jets bend gracefully or crumple into knots? Every new discovery peels back another layer, revealing that even the universe's most violent processes might follow patterns we're only beginning to trace. And somewhere out there, in the silence between the stars, another X might be forming, a cosmic signature waiting to tell its story. Somewhere in the depths of intergalactic space, an invisible force is tugging at our galaxy and everything around us, with a pull so strong it defies conventional explanation. This is the Great Attractor, a gravitational anomaly so massive that it's dragging the Milky Way and thousands of neighboring galaxies toward it at over 14 million miles per hour. The strangest part, we can't even see what's causing it. Located roughly 250 million light-years away in the direction of the constellations Centaurus and Norma, the Great Attractor lurks behind the dense plane of our own galaxy, shrouded by cosmic dust and stars that obscure our view. At first, astronomers thought this mysterious force might be a single, unimaginably massive object, a hidden supercluster of galaxies, or even a gargantuan black hole dwarfing anything we've ever discovered. But as telescopes peered deeper, a more complex picture emerged. The leading theory now suggests the Great Attractor isn't one thing, but many, a sprawling confluence of galaxy clusters known as the Laniakea supercluster, a web of gravity binding hundreds of thousands of galaxies together in a vast celestial river. At its heart lies the Norma cluster, a dense knot of galaxies so packed with dark matter that their combined gravitational influence reaches across unfathomable distances, bending the paths of galaxies like ours like leaves caught in a cosmic current. Yet even this explanation leaves gaps. The motion we observe requires more mass than visible matter can account for, hinting that something even larger, perhaps an entirely unknown structure, lies beyond the Great Attractor, pulling it in turn. Some researchers speculate about the Shapley Attractor, a supercluster 500 million light-years distant, whose gravity might be adding to the tug of war. Others wonder if dark matter, the invisible scaffolding of the universe, is clustered in ways we don't yet understand, amplifying this relentless drift. What makes this mystery so compelling isn't just the scale, it's the implications. If the Great Attractor is part of a hidden hierarchy of cosmic structures, it means our corner of the universe is far more dynamic than we once thought, caught in flows of gravity that stretch across billions of light years. And as new telescopes like Euclid and the Vera Rubin Observatory map the sky in unprecedented detail, we might finally lift the veil on what's pulling us and where this invisible river is taking us next. Imagine a galaxy so perfectly symmetrical it looks like a cosmic bull's eye, a shimmering ring of blue stars circling a golden core with an eerie void in between. That's Hoag's object, a celestial oddity discovered in 1950 by astronomer Art Hoag, who initially mistook it for a planetary nebula. But this wasn't just another pretty space cloud. It was an entirely new class of galaxy, one that defied every conventional explanation for how these colossal stellar systems form. What makes Hoag's object so baffling isn't just its beauty, it's the fact that it exists at all. Most galaxies fall into familiar categories: spirals with winding arms, ellipticals like giant cosmic blobs, or messy irregulars. But ring galaxies like Hoag's object are vanishingly rare, making up less than 0.1% of known galaxies. The textbook explanation for ring structures involves a violent collision, one galaxy punching through another, sending shockwaves that compress gas into a starburst ring. The iconic Cartwheel Galaxy is a prime example, its unmistakable spokes and ripples betraying a past cosmic crash. Yet Hoag's object shows no signs of trauma. There's no debris, no distorted core, no neighboring galaxy that could have been the culprit. It's just perfect. So how does a galaxy like this form without a catastrophic intervention? One theory suggests a slow, internal reshuffling of matter. If a central bar of stars, a common feature in spiral galaxies, became unstable over billions of years, it might have funneled gas outward until it pooled into that pristine ring. The problem: Hoag's object lacks any trace of a bar or residual spiral structure, leaving this idea on shaky ground. Another possibility involves gravitational instabilities, subtle ripples in the galaxy's disk that amplify over time, sculpting the ring naturally. But simulations struggle to produce something this symmetrical without outside help. Then there's the enigma of the void. Unlike most ring galaxies where the center glows with older stars, Hoag's object features a gap so clean it feels almost engineered. Some researchers speculate this could be the work of an ultra-rare resonance, where the orbits of stars and gas align in just the right way to clear that space. Others wonder if a second, fainter ring might lurk in the darkness, undetected by our telescopes. Even more intriguing, in 2021, astronomers spotted another potential ring galaxy floating near Hoag's object, a possible cosmic sibling that, if confirmed, could hint at an entirely unknown formation mechanism. What makes Hoag's object more than just a curiosity is what it reveals about the universe's creativity. Here's a galaxy that shouldn't exist by our current rules, a cosmic rebel that forces us to question whether we've underestimated nature's ability to craft perfection without violence. Every new observation peels back another layer of mystery, reminding us that for all our theories, the universe still holds blueprints we've yet to decode. And somewhere out there, other perfect rings might be waiting silent, sublime, and daring us to explain them. Deep in the constellation Monoceros, about 2,300 light-years from Earth, a cosmic jewel box glows with an eerie crimson hue, the Red Rectangle Nebula. But this isn't just another pretty cloud of gas. What makes it extraordinary isn't its color, it's its shape. Viewed through powerful telescopes, the nebula doesn't billow in amorphous wisps like most stellar remnants. Instead, it forms a near-perfect X, its crimson arms stretching outward like the ribs of an hourglass, framed by a rectangular halo of dust so precise it looks almost sculpted. This isn't random chaos, it's geometry written in starlight, and the secret behind its symmetry lies in the frantic dance of two dying stars at its heart. The Red Rectangle's bizarre structure starts with its central binary system, HD 44179. Here, a dying sun-like star orbits a hotter, younger companion in a gravitational waltz so tight their year lasts just 10.5 months. As the aging star sheds its outer layers, its partner's fierce stellar winds carve that expelled material into opposing cones, twin jets of gas and dust funneled into space by the binary's rotation. But gravity doesn't just shape these outflows, it twists them. The star's orbital motion wraps the expelled material into intricate spirals, while dust grains aligned by magnetic fields polarize the light, intensifying that signature red glow. The result, a cosmic loom weaving stardust into that unmistakable X. Yet even this explanation doesn't account for the nebula's sharp edges. Most planetary nebulae, the glowing shells of dying stars, expand into space as diffuse spheres. The red rectangle's crisp line suggests something more, a vast disk of cold dust and molecules, invisible to optical telescopes but revealed by infrared observations, constraining the outflow like a celestial cookie cutter. This disk, spanning over 8,000 times the distance from Earth to the Sun, acts as a stencil, forcing the ejected gas into that rectangular silhouette while the binary star's motion etches the X within it. But the mystery deepens when we examine the nebula's chemistry. The red rectangle isn't just red, it's one of the richest known sources of complex organic molecules in space. Spectroscopic studies have detected polycyclic aromatic hydrocarbons, PAH, carbon-based compounds, also found in soot and interstellar clouds shimmering throughout its structure. Some scientists speculate these molecules might form in the turbulent shocks where the binary star's winds collide, creating a cosmic laboratory for prebiotic chemistry. Could nebulae like this have seeded the galaxy with the building blocks of life? The most tantalizing question, though, is how common such geometric perfection might be. For decades, astronomers assumed the red rectangle was a fluke, until Hubble and other telescopes began spotting similar X-shaped nebulae, like the one surrounding the star HD 89353. Each discovery suggests that binary star systems might sculpt their death shrouds into precise shapes far more often than we realized, hidden from view until the angle of observation reveals their symmetry. What makes the red rectangle more than just a cosmic oddity is what it teaches us about chaos and order. Even in the violent throes of stellar death, the universe finds ways to impose geometry, turning chaos into art through the silent pull of gravity and spin. And somewhere out there, other dying stars might be painting their own celestial masterpieces, waiting for us to train our telescopes their way. Out in the direction of the constellation Boötes, there's a place where the universe feels eerily empty, a spherical void so vast it could swallow thousands of galaxies whole, yet it holds almost nothing. Stretching 330 million light-years across, the Boötes void is one of the largest known structures in the cosmos, a cosmic desert where galaxies are so sparse that if you stood at its center, you might look up to a night sky with barely a dozen stars visible to the naked eye. For comparison, our own Milky Way neighborhood teems with thousands of galaxies in a space this size. The Boötes void shouldn't exist, at least not according to our best models of how matter clumps together after the Big Bang. When astronomers first mapped this region in the 1980s, they expected to find the usual tapestry of galaxy clusters and filaments, the web-like structure that defines the observable universe. Instead, they found a staggering absence. Out of the 60 galaxies initially detected in the void, most huddle along its edges, as if clinging to the shores of an unfathomably deep lake. The few galaxies drifting inside are isolated oddballs, anemic, starved of the gas needed to birth new stars, their evolution frozen in a state of cosmic loneliness. This isn't just a quiet corner of space, it's a place where the rules of galactic life seem rewritten. So how did such a void form? The leading theory points to a runaway chain reaction of mergers billions of years ago. Imagine multiple galaxy clusters, each pulling others into their gravitational embrace over eons, leaving behind vast, emptied bubbles in their wake. As galaxies clumped together, the space between them stretched into these desolate voids, but the Boötes void is too big, too empty to fit neatly into that explanation. Simulations of cosmic structure struggle to produce voids this extreme without invoking something else, perhaps a primordial fluctuation in the density of the early universe, a rare underdense region inflated to monstrous proportions by the rapid expansion of spacetime itself. Yet even that raises questions. If the void is truly ancient, why haven't nearby structures flooded it with galaxies by now? Some researchers speculate that dark energy, the mysterious force accelerating the universe's expansion, might be actively pushing matter away, keeping the void hollow. Others wonder if we're seeing the ghostly imprint of an even larger phenomenon, a supervoid so immense it warps the light passing through it, distorting our observations. Then there's the tantalizing, if controversial idea that the Boötes void isn't entirely empty. Radio telescopes have detected faint whispers of hydrogen gas threading through the darkness, and a handful of dim, dwarf galaxies might lurk unseen. Could these be the survivors of a once thriving population, their larger siblings long since cannibalized by the void's hungry edges? Or is this gas the residue of galaxies that never fully formed, stunted by some primordial defect in the fabric of spacetime? What makes the Boötes void more than just a curiosity is the way it forces us to question our assumptions. If voids this vast can exist, how many others might we have missed? Could they be the fingerprints of physics we don't yet understand, or even gateways to something stranger, regions where dark matter behaves differently, or where the constants of nature subtly shift? For now, the void keeps its secrets, a silent reminder that the universe isn't just a tapestry of light, but also of shadow. And in those shadows, the most profound mysteries might still be waiting. The universe isn't just expanding, it's accelerating, flying apart faster with each passing second, as if some invisible hand is pressing hard on the cosmic gas pedal. This startling discovery, made in the late 1990s by observing distant supernova, earned its Nobel Prize but left astronomers with an even deeper puzzle. What unseen force could possibly overpower gravity itself? The answer, for now, rests in a placeholder named dark energy, a term that hides our profound ignorance behind two simple words. What makes dark energy so baffling isn't just its dominance. It makes up roughly 68% of the universe's total energy budget, but the way it defies intuition. Unlike matter or radiation, which dilute as the universe expands, dark energy appears to maintain a constant density, as if new energy is continuously conjured into existence to fill the growing void. Imagine stretching a rubber band and watching it grow thicker instead of thinner. That's the counterintuitive reality we're grappling with. The leading theory, known as the cosmological constant, traces back to an idea Einstein once called his greatest blunder. It suggests empty space itself contains intrinsic energy, a kind of anti-gravity woven into the fabric of reality. Quantum physics predicts this vacuum energy should exist, but there's a glaring problem. Calculations of its strength overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science. Some researchers argue this points to undiscovered cancellation mechanisms or flaws in our quantum theories, while others propose dark energy might evolve over time, changing strength as the universe ages. Then there's the radical alternative, quintessence. This hypothesis imagines dark energy as a dynamic field permeating space, its energy density shifting like a cosmic mood ring. Unlike the rigid cosmological constant, quintessence could interact with other forces or even clump unevenly across the universe, leaving faint fingerprints in the large-scale structure of galaxies. But despite decades of searching, no such variations have been found, leaving the field largely theoretical. Even more speculative ideas push the boundaries of known physics. Some theorists suggest dark energy might signal extra dimensions curled up in ways we can't perceive, leaking gravitational influence into our four-dimensional world. Others propose it's an illusion created by our vantage point. that what we perceive as acceleration might actually be light bending through uneven regions of spacetime, a trick of perspective on cosmic scales. The stakes couldn't be higher. If dark energy strengthens over time, it could eventually tear apart galaxies, stars, and even atomic bonds in a big rip. If it weakens, gravity might regain dominance, collapsing the universe in a fiery, big crunch. Or it might continue its gentle push, leaving the cosmos cold and dark but intact. Current projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map billions of galaxies, hunting for subtle changes in expansion rates that could reveal dark energy's true nature. What makes this search so electrifying is its humility. Dark energy reminds us that nearly all the universe is made of stuff we can't see, can't touch, and barely understand. It's the ultimate cosmic joke. Just when we thought we were figuring things out, the universe handed us a blank check labeled dark energy and dared us to fill in the amount. And somewhere in that emptiness, the answer waits not just to what drives the cosmos apart, but to what it truly means that we're along for the ride. Rising like ghostly echoes from the heart of our galaxy, two vast orbs of radio energy stretch above and below the Milky Way's core, smaller, stranger siblings to the Fermi Bubbles, but no less mysterious. Discovered in 2019 by the Mercator Radio Telescope in South Africa, these so-called galactic center radio bubbles span 1,400 light-years each, their smooth, almost perfectly rounded edges glowing with synchrotron radiation, a telltale sign of electrons spiraling at near light speed through powerful magnetic fields. Unlike their gamma-ray emitting cousins, these bubbles don't radiate visible light or X-rays. They hum quietly in radio frequencies invisible to most telescopes until now. But what's truly astonishing isn't just their size or symmetry, it's the timing. These bubbles are young by cosmic standards, likely no more than a few million years old, suggesting our galaxy's supermassive black hole, Sagittarius, a star, might have recently staged a violent performance we just missed witnessing. The leading theory points to a cataclysmic outburst, a moment when Sagittarius, a star, awoke from its usual slumber to devour an enormous clump of gas or even a wandering star. Such a feast would have unleashed jets of plasma, inflating these bubbles like cosmic balloons in a process similar to blowing smoke rings. But here's the puzzle. The bubbles' pristine, unbroken shapes imply a single, explosive event rather than the messy, ongoing activity we see in other galaxies. It's as if the Milky Way's black hole coughed once, violently, then fell silent again, leaving behind these perfectly preserved radio echoes. Supporting this idea are X-ray observations of the galactic center, which reveal faint shockwaves rippling through nearby gas clouds, footprints of the same ancient explosion. Yet not every clue fits neatly. The bubble's energy distribution is oddly uniform, lacking the chaotic variations you'd expect from a black hole's erratic feeding habits. Some researchers propose an alternative origin, a frenzy of star formation near the galactic center, where hundreds of supernovae exploding in quick succession could have pumped enough energy into the interstellar medium to carve out these structures. It's a compelling idea, except for one hitch: the bubble's symmetry. Stellar explosions are messy affairs, rarely producing such perfectly matched structures. Then there's the wild card, dark matter. A minority hypothesis suggests these bubbles could be the aftermath of annihilating dark matter particles colliding near the galactic center, their decays producing the electrons that now light up the radio sky. While speculative, the idea isn't entirely far-fetched. The Milky Way's core is thought to harbor a high concentration of dark matter, and its interactions could, in theory, leave behind such ephemeral fingerprints. What makes these radio bubbles so captivating isn't just their origin story, it's what they reveal about our galaxy's temperament. Unlike active galaxies with raging black holes, the Milky Way is usually a quiet neighbor. These bubbles are a reminder that even calm cosmic islands can have violent pasts, and that Sagittarius, a star now dozing, might one day wake up hungry again. For now, they float silently above us, twin monuments to a cataclysm we barely glimpsed, whispering secrets about the dynamism hidden in even the most familiar corners of the cosmos. Beyond the known planets, lurking in the icy darkness past Neptune, something massive might be warping the orbits of distant objects, tugging at them with a gravitational hand we can't yet see. This is the tantalizing mystery of Planet 9, a hypothetical world 10 times the mass of Earth, proposed in 2016 by astronomers Konstantin Batygin and Mike Brown to explain a series of bizarre orbital alignments in the outer solar system. The clues began stacking up when researchers noticed that several extreme trans-Neptunian objects, icy bodies like Sedna, and 2012 VP113 shared strangely tilted orbits that clustered in unexpected ways, as if herded by an unseen giant. The math is compelling. Advanced simulations show that without an additional massive object, these orbits should be randomly scattered. Instead, they swing in concert, their closest approaches to the Sun grouped in space, a pattern with less than a 0.2% chance of happening naturally. Even stranger, some of these objects orbit backward, tilted at extreme angles compared to the rest of the solar system. A distant, undiscovered planet could account for these anomalies, its gravity sculpting their paths over billions of years. But where is this hidden world? The search zone spans a vast swath of sky, roughly 20 times wider than the full moon, in the dim reaches of the constellation Orion. At an estimated distance of 400 to 800 astronomical units so far that sunlight would take days to reach it, Planet 9 would be frigid and faint, reflecting almost no light. Current telescopes like Subaru and the Vera Rubin Observatory are scanning these shadows, hunting for the faintest glimmer of motion against the static stars. Every passing year without a detection tightens the constraints, narrowing where it can't be, but the possibility remains. Not everyone's convinced, though. Alternative explanations range from a primordial black hole no larger than a grapefruit whose gravity could mimic a planet's, to the collective pull of countless smaller objects in the Kuiper belt. Some models suggest a distant disk of icy debris with a combined mass 10 times Earth's might warp orbits just as effectively. Others argue observational bias. Maybe we've only found clustered objects because telescopes are looking in the wrong directions, missing a fuller, random distribution. Then there's the wildest twist. What if Planet 9 isn't a planet at all, but a captured rogue, a free-floating world, born around another star and snatched by the Sun's gravity in a cosmic game of orbital pinball? If true, it would be a fossil from another solar system, a refugee hiding in plain sight. The hunt continues, fueled by each new discovery of a far-flung object with a wonky orbit. Whether Planet 9 is out there or not, its ghostly influence, real or imagined, has reshaped how we see our solar system's edges. It's a reminder that even in our own celestial backyard, the universe might still be hiding giants. For decades, the twin Pioneer spacecraft held a secret, one that threatened to upend our understanding of gravity itself. After their historic journeys past Jupiter and Saturn in the 1970s and 80s, Pioneer 10 and 11 continued drifting toward the edge of the solar system, their faint radio signals meticulously tracked by NASA, a deep space network. But by the late 1980s, something peculiar emerged in the data. Both probes were slowing down ever so slightly, as if an invisible hand were gently tugging them back toward the Sun. This tiny deviation, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, and for years it haunted physicists like an unsolved equation. At first glance, the numbers seemed to whisper heresy. The deceleration matched no known force in Newtonian or Einsteinian physics. Some speculated about undetected gas clouds or dark matter's gravitational drag. Others dared to suggest modifications to gravity itself, new physics that would ripple through textbooks if proven true. The anomaly was minuscule but persistent, appearing in datasets spanning decades, and it refused to vanish no matter how researchers crunched the numbers. Then came the thermal hypothesis, a solution as elegant as it was mundane. The Pioneer probes weren't just passive travelers, they were powerhouses of heat, their plutonium-fueled generators radiating warmth into the void. Engineers realized this energy wasn't escaping uniformly. The spacecraft's dish-shaped antennae acted like mirrors, reflecting thermal radiation preferentially in one direction, backward toward the sun. Every photon bouncing off carried a tiny kick, a recoil effect that, over billions of miles, added up to that mysterious deceleration. It was rocket science in reverse heat acting as an invisible thruster, slowing the probes imperceptibly. The clincher arrived when sophisticated thermal models of the spacecraft matched the anomaly's exact magnitude. Even asymmetries in heat distribution, like warmth leaking from electrical components, accounted for subtle variations in the data. By 2012, after exhaustive analysis, most of the scientific community agreed. The Pioneer anomaly wasn't evidence of new physics, but a masterclass in how even the tiniest overlooked details can ripple across cosmic distances. Yet the story holds a deeper lesson. What began as a potential revolution in physics became instead a celebration of human ingenuity, our ability to spot anomalies, question assumptions, and chase answers from the quantum to the cosmic. The Pioneers, now silent and drifting toward interstellar space, left behind more than just data. They reminded us that sometimes the universe's greatest mysteries aren't written in the stars, but in the delicate interplay of heat, metal, and motion. And that solution, as it turns out, was hiding in plain sight all along. Deep in the afterglow of the Big Bang, there's a pattern that shouldn't exist, a ghostly axis stretching across the cosmos, silently defying our most fundamental assumptions about the universe's birth. This is the so-called axis of evil, a bizarre alignment in the cosmic microwave background, or CMB, that has haunted cosmologists since its discovery in 2005. The CMB is humanity's oldest family photo, the faint microwave glow left over from when the universe was just 380,000 years old, a baby picture showing the first light streaming through the newborn cosmos. According to the Standard Model, this radiation should be evenly distributed, its temperature fluctuations random and isotropic like static on an old TV. But when scientists mapped the CMB with unprecedented precision using satellites like WMAP and Planck, they found something unsettling. The hot and cold spots weren't entirely random. Instead, they showed a curious preference, aligning along a specific axis that points toward the constellations Leo and Aquarius, a cosmic fingerprint that, if real, shouldn't be there. The implications are staggering. If the universe has a preferred direction, it violates the cosmological principle, the foundational idea that, on large scales, the cosmos should look the same in all directions. It's like discovering that all the trees in a vast forest inexplicably lean toward the same compass point. Some theorists suggest this alignment could be a relic from before the Big Bang, a scar from some primordial asymmetry that imprinted itself onto space-time. Others propose even wilder ideas, like our universe being caught in the gravitational wake of a neighboring bubble universe, its pull distorting the CMB like a ship's wake disturbing still waters. But before we rewrite physics textbooks, there's the ever-present specter of observational bias. Could this axis simply be an illusion? One leading critique points to the Doppler effect from our solar system's motion through the CMB. As Earth hurtles through space at over 370 kilometers per second, this movement could subtly skew the data, creating a false axis in the same way a speeding car makes raindrops appear to slant. However, when researchers corrected for this motion, the alignment stubbornly persisted. Other skeptics argue that human perception plays tricks, that we're wired to find patterns even in randomness, like seeing faces in clouds. Statistically, some apparent alignment is inevitable given the sheer number of ways to slice the data. the plot thickens when we examine the CMB's other anomalies. The northern hemisphere's fluctuations appear slightly stronger than the southern, and there's a mysterious cold spot spanning billions of light years that defies easy explanation. Taken together, these oddities suggest either a universe far stranger than we imagined or systematic errors in our measurements that we haven't yet uncovered. Future missions, like the upcoming CMB-S4 project with its ground-based telescopes in Chile and Antarctica, aim to settle the debate with even finer resolution maps, hunting for distortions at smaller scales that could confirm or refute the axis once and for all. What makes this mystery so compelling isn't just the science, it's the philosophical weight. If the axis of evil is real, it hints at a cosmos with built-in directionality, a universe that remembers its past in ways we can't yet fathom. Or perhaps it's a cosmic prank, a reminder that even our most precise instruments are still learning to see. Either way, this faint whisper from the dawn of time challenges us to question not just the universe's structure, but the very foundations of how we understand it. And until the next generation of experiments weighs in, the axis remains a silent question mark etched across the sky. From the fleeting whispers of the wow signal to the cosmic choreography of the Great Attractor, these 30 unexplained galactic phenomena remind us just how vast and how strange our universe truly is. We've traced the footsteps of rogue objects like Oumuamua, marveled at the perfect geometry of Hoag's object, and even dared to ask if signals like Arecibo 02 plus 14 could be messages from civilizations beyond our own. Yet for every mystery we've unpacked, a dozen more questions emerge. Why do some fast radio bursts repeat while others vanish without a trace? What unseen force tugs at galaxies in the dark flow? And is dark energy quietly rewriting the fate of everything? The beauty of these enigmas isn't just in their complexity, it's in what they reveal about our place in the cosmos. Each signal, each anomaly, is a reminder that the universe is far from finished surprising us. The theories we've explored, from colliding neutron stars to alien megastructures, aren't just wild guesses. They're stepping stones, ways for us to stretch our imaginations while clinging to the rigor of science, because sometimes the most outlandish ideas lead to the most profound truths. So what's next? Maybe you'll be the one to spot a pattern in the chaos, or to question a theory that everyone else takes for granted. The universe is still speaking, through radio whispers, infrared glows, and gravitational ripples, and it's up to all of us to listen. If these mysteries have sparked your curiosity, hit subscribe and join us as we dive deeper into the unknown. And don't forget to share your favorite theories in the comments below. Is there a signal we missed, a cosmic oddity that keeps you up at night? The conversation doesn't end here, it's just getting started. After all, the greatest discoveries begin with a single question: what if?